Good day, everybody. In this session, we're going to have a quick review and some of my thoughts around systems, information systems, with a specific focus on hardware and software. I'll focus more on the software piece. I think that's the more interesting piece to meet the objectives of this class. But I want to make sure that we learn a little bit more about the key hardware areas that influence software and software development, particularly in the context of business systems. So the, the building blocks of any technology project, any information technology project is fourfold. We start with hardware, and that can come in local hardware or distributed hardware across the intranet or internet. We've got, of course, the more interesting piece where a lot of work and a lot of expenditure takes place, which is software development. We have networks, which by and large we are going to skim in this course because it's not the area of focus. And we will, in a later session, talk a lot more about data, databases, data files, and how they play in the successful build out of information systems projects. So hardware, as we discussed in the last session, are physical pieces of a computer system. Software is a set of programs, very simply put, that control the operations of a computer. Now, if we look at the basic components of a computer system, you have essentially a processing control unit. You've got some arithmetic logical operations going on. There's storage, there's memory, and that's considered internal storage. And then we have files, which are generally external storage. And then we have some input, whether it be data, some kind of event, and then that gets processed by the central processing unit, and then you have output, which could be a screen output, it could be a report, it could be deliverables, it could be some sort of signals, either digital or analog. It doesn't matter for this discussion. But this is the basic sort of blueprint of a computer system. If we move to software, software come in many varieties, but to simplify, there's two categories: application software and support software. Application software sits on the top. It's the more client-facing or user-facing layer of software. We've also got the operating system, so analogous to iOS, analogous to Microsoft Windows, Linux. Those are the kinds of operating systems that are in play today. There's some open source ones, there's some proprietary ones, and so on and so forth. And then we have support software that support these systems and applications that we've been discussing. Application software, we can think of many examples. A simple one is like an accounting software package. And you can have personal productivity software like Microsoft Word, Microsoft Excel, and so on. You've also got database systems, you've got graphic systems, you've got CAD systems. There's a variety of applications that you're probably using. For example, if you do taxes on your computer, you might be using TurboTax. That's an example of a personal productivity software and could be purchased off the shelf, so on. Email an email client like running Microsoft Office on your computer is an example of productivity software. And there's a variety of database softwares that control or can be accessed, and their database is a shared collection of data, generally logically grouped. Doesn't always have to be logically grouped, but generally a logically grouped set of data containers, if you want to call them that. And the most common database system that's in play is called the relational data model. We'll be discussing the innards of relational data models in a later session in this course. But for now, it suffices to say these are samples of application software that are in play in today's environment. Graphical softwares, for example, PowerPoint. You might have seen a video editor that you might use on your phone or on a desktop to create audio or video files. Many people are doing karaoke on their computers by connecting their karaoke client software to others around the world, and they're able to actually sing songs together, distributed all over the world, and record them and actually make them public on YouTube and so forth. I found that fascinating as I myself experienced and played along with that as a hobby over the last few months as we've been locked down in the COVID environment. So lots of great uses for personal applications of these kinds of software systems. I think I mentioned emails already. Again, an example is the Outlook app that most of us use. I know I use it to access my Fairfield email, both on my computer and on my phone. And that's an example of a personal productivity software application. Browsers are another, we don't think of browsers as an application, but browser is an application, literally a software application that connects us to the internet, connects us using pull and push technology, things like Explorer, Firefox, Safari, Chrome. I use Chrome a lot. Many of you probably use Chrome as well, offered by Google. These are also examples of application software. Support software enables application softwares to be carried out, right? So these programs and applications that I mentioned are written in a variety of languages, and they can be purchased from hardware or software vendors. There are some vendors that offer both the hardware component and the software component. Not always, but they're obviously there, like an IBM, like a Microsoft. They make hardware, they also make software. Now, if we look at the languages, the programming languages that power some of these softwares, when I became a programmer 30 years ago, I started by learning machine language and assembly language. That is generally how the most basic of software is coded for speed. These languages, the earlier generation languages are fast and furious, but they're very difficult to learn, to master, and to code in, right? So you don't see a lot of this happen now in business software. You don't see a lot of these languages being used in business software, but they are used in creating operating systems and base software that power computers. As I've noted here, they can be tedious, they can be time-consuming, and they're not generally used for business applications. They're used for, like I said, the backbone of software that actually runs the business application software. And this just shows how assembly language, then if it's written in assembly language, this kind of software example that we're talking about, it then gets translated into machine language. Machine language is then created or it functions as an object program which can be directly executed without any further translations by the computer. Machine language is basically bit and byte instructions to quickly get processed by the processor, the CPU, the central processing unit, and use very minimal storage, so it's super duper fast. So any languages that we're going to talk about past the first generation, which is machine language, like the second generation, the third, and the fourth, and that I'm about to talk about in a few minutes, they all get ultimately translated to machine language. And because there's a translation process, they tend to be a little slower. Now, we don't care about speed as much in today's environment because, as I mentioned earlier, hardware has been increasing in sophistication and in quality and in cost, right? The cost is a lot favorable. You can buy better and better hardware for cheaper and cheaper prices. So hardware is generally not the issue, and therefore we can write code in more advanced third generation languages where we can start to write more English-like um, instructions that then get translated to the machine language that can then be processed by the computer hardware, right? And typically when we start to operate in third, fourth, and fifth generation, or sorry, third and fourth generation languages, we can make the code a little bit more machine independent. That means it's easier for programmers to learn. We can train programmers quicker. Programs are structured, they're divided into modules so many people can work on them at the same time. And these also get compiled and interpreted and again, reduced down ultimately to the machine language instructions that we were talking about just a few minutes ago. And this is basically an overview. I don't want to spend too much time on how that translation happens, but it suffices to say that you code it in the high level language and then a compiler then uh, translates it into that machine language, and data is fed in uh, into the program when the program runs, and you execute, and then you generate some sort of output that we were talking about. So um, when you're developing programs in a 3GL or higher, there you can have a very structured approach to the development process because you're not inundated by writing machine code. Your programmers and your technology staff actually have time to spend on identifying the problem, figuring out how to code it, which I would simplify as algorithm development, converting that over to a structured sort of pseudocode, what we call pseudocode, which is a precursor to the actual code. Then the program gets prepared. Then somebody, namely the programmer usually, and the programming team, types this in or somehow enters this code, the program that gets compiled. We use test data to see if it works. We debug it because it's not going to work always, and you have errors, so you do a testing process, and then you use actual data. And this is the progression of the development process that we are able to enjoy. And as you can see, as we have data, we have test data, we have actual data, that means we are getting closer and closer to the business and making sure that the programs that we're coding run properly with the actual data that's supplied from the business um, elements, which namely are people as well as other technologies that the business is already using. So coding in higher level languages frees our time up, gives us a, a, a enables a more structured way of developing these software packages or software modules in a way that meet the business needs. And we know that when it meets the business needs, the business is likely to fund these projects, and we're likely to have more of these projects, and therefore our IT group grows productively and are valued as strategic partners because they're creating these programs that actually ultimately meet the needs, increasingly meet the needs as time goes on. These used to be the most popular procedural languages. They're still used, but very minimally at this point. Most of business applications aren't done in these third generation languages. We've sort of moved from these cryptic program, and these used to be, I mean, this is how I learned my programming on COBOL and Fortran, namely. And this was actually considered super easy back then. And as you can see, you can probably read it if you're not a programmer. You can start to understand this just by taking a good look at it. If you took a 5-minute look at this, you'll start to understand what this program is starting to do in some sense. It's very readable. If I were to show you the machine language equivalent of this, all you would see is zeros, ones, A, B's, C's, D's, and F's, right? And that would not be readable. But this is pretty readable. I can train any of you to run a COBOL program by the end of the week if I had to, because it's not much more complicated than what you see here. We then go to fourth generation languages, which are even easier to program, use more English-like statements, and are very rapid in their evolution as well as their use. So we also then have markup languages, for example, HTML, many of you have heard of. These are used to create web pages. They're just basically tags. We use the word markup languages because they're even easier than programmer languages, so to speak, because all we're doing is really tagging elements or text or graphics so that they show up in a certain way, right? Like, for example, a hyperlink or a clickable picture and so on. And XML is used to facilitate data exchange with web applications and web services. It's sort of a metadata version of HTML, and it uses tags to identify in a standard way particular data elements that can then be used by applications uniformly, right? So it's a sort of a ease of transfer of data and information from one system to another, even across business units or across companies. Here's an example of an XML tag that focuses on a soccer game and displaying of scores. Object-oriented programming are not procedural in nature. They are object-based, which means that we create objects once, we store them, we test them, and then we reuse them. So for example, a checkbox. You might have seen how on Microsoft, checkboxes appear kind of similarly on Word and Excel and PowerPoint. If you've used those applications, you can see that the object called checkbox is pretty standard. People understand how to use it, what it means. You also know what a text box means. So when Microsoft is coding, just as an example, these applications that use text boxes, they're using a standard built-in framework internally that they've vetted, tested, and included all the right fonts and so on. So they encapsulate all of that in a particular text box, and then they use it across their different applications. So not only their programmers facilitated using those, but users understand it because they understand what a text box is and when to use it. They understand what a checkbox is, and so on. And so the father of object-oriented languages was C++. That's how I learned it first. It was an extension of C. It was the object-oriented version of C. And from there on, we've expanded to many, many different types of or additional languages that are OO and reuse focused, right? And here's a sample of what object-oriented programming looks like in the Java application. You've got a particular function or a class that's being defined. It's called dog, and it has some standard functions, sleep, run, and so on. And it encapsulates, and it's very easy to read. And the compiler then reduces this to what you really want the function to do at execution time, right? So it gets compiled and then it gets interpreted just like the third and fourth generation languages that gets reduced to ultimately machine language, right? But this obviously takes a lot of CPU time or a lot of compiler sophistication, but all that can be processed quickly because, as I mentioned earlier, hardware has been increasingly optimized to handle sophisticated programming languages like this so that they're easier for the business to create. They're easier for programmers to work with business to create these objects or object-oriented constructs and enable reuse, which means we're not reinventing, in my other example, the text box over and over again, for instance. Web applications are prevalent, as you know. We've experienced the use of banking applications and many other applications that you can think of that operate on the web. Basically, any function that you do using a browser, you are using a web application. And HTML is the most common interface that's used so that every browser recognizes it. And then there's many other languages. For example, the server-side programming languages like PHP, Java servlets, etc., that are used to create those apps that run ultimately on those servers, right? And they access data and they present it to us all in the browser. We're going to talk more about database management systems, but Those are systems that create and store and manage data and a database. And so you can query off of those data, you can report off of them. When you design databases, you are generally starting with a data dictionary, which is a repository of what everything means, what columns and rows are you going to store, what constructs are you going to store in these databases, and typically we start with a data dictionary. Now, many systems out there, the workplace may not even have a data dictionary, but increasingly most systems that are developed with common uh, development methodologies or more popular development methodologies are ensuring that data dictionaries exist, so everybody knows where to find information and what shape the information is in, what are the different attributes of that information, and so on. Data warehouse is a very large collection of these databases that are used kind of in an archive mode to enable quick access. They're not the transactional databases that we talk about or users use to run the business, but they're used for generally for analytics, for reporting, and as such, these large, call it historical databases or active archives of these of the transactional database, they're optimized for using sophisticated data mining applications and so on. If you did those things on a transactional database, you could potentially slow down everyday business. Therefore, users or companies, IT organizations create these warehouses to do those kinds of analysis. There are many different types of um, database architectures, right? The 5 most popular are hierarchical, networked, relational. By far the most common is the relational database. And we have object-oriented databases that store large globs of graphics, videos, and so on. And then there's the hybrid, which is the object relational database. We're going to talk a lot more about this in a few sessions from now. And we're going to do a case study and example on a relational database. And finally, if you have a query in common querying language that you use in a database, like a relational database, is SQL. And this is a sample SQL statement that selects the order number, the customer, and the date and the name from a particular table called customer and order. And it joins the customer and order by number so that it relates those two in those two tables where the order date is greater than March 12th. Okay, so this will return all of the appropriate data that you want from the database. And it's as simple as that to write a SQL statement. There are many graphical tools that help you actually point and click instead of coding this kind of statement. And by the way, these statements can get pretty complicated, right? This one's a simple one for illustration purposes. But for those of you who've seen or experienced complex queries inherent in reports and in other BI tools, many times you've got a SQL statement that spans pages and pages of code that looks something like this with more attributes, and that gets executed to go and quickly grab the data from the database. Okay? So most database systems have some sort of querying tool or language or protocol, and this is the most common one, SQL, that retrieves the data essentially. And these SQL statements can then be wrapped around or wrapped within larger programming constructs, either those third, fourth generation languages that we were talking about, or an object-oriented wrapper that gets the data repeatedly in the same way, in a tested way, so that the application functions correctly. There's case tools. I don't want to talk too much about these, but collection of software tools kind of automate the different software development lifecycle steps to increase productivity of the software developers that are creating this software. There's communication interface software. There's FTP protocols that are used for just transferring files from one computer to the other in a safe and secure way, and so on. Key software trends that I think you will agree with and will resonate as well is there's a a lot of concern for not spending too much time or being more efficient in how we create software. So IT resource is expensive, so there's a lot of push to create more efficiencies, which means create better languages, more reuse, so that people can generate software that's high quality in a quicker fashion. Therefore, many people are concerned, looking at trends or experiencing trends in increase of purchasing software. There are companies like Oracle, the company I work for, Salesforce, SAP, you name it, Microsoft. All of the major players are offering application software that's tested and made for fit for purpose. You just buy it and implement it, or configure it. And the promise is to be more efficient and get your money's worth quicker than if you would, as a company, try to build it. Open source software exists. A lot of people are concerned about safety, but many of these industrial software systems are actually based on open source. Open source is a way of people collaborating together across the world using technology to create software that's software components that are freely available, right? And people can use it, deploy it, and extend them without cost, without per unit cost. They might be cost in customizing or implementing or testing it, but the actual code somebody wrote in the spirit of adding to the overall database or overall proficiency of these softwares. Object-oriented obviously is a trend for all the reasons. More user development, more things running on intranets, and a lot of increase in personal productivity software. So these are some of the trends. Hardware firms have been expanding, adding services. There are major players in this, all the names that you might recognize. Software firms are also consolidating, getting bigger, getting more creative, and highly competitive, right? And so on. This statement here is incorrect. I think Oracle tried to buy Salesforce, but has not bought Salesforce yet. I wish they did. They're a big competitor, but Oracle did buy PeopleSoft and others, and many of these companies, including IBM and others, are in deep acquisition mode. The last thing I want to talk about today is this concept of reuse, right? We've alluded to it several times. I want to just explain reuse for a second. Reuse implies the use of previously written software, right? And it is prevalent and most noted in object-oriented development. That's the whole impetus behind object-oriented development, right? You develop these object classes, you create common behavior that you can figure out, you define common entities, for example, employees, and you define the functions that employees do or you do to employees as a firm, and then you make that available in different applications so that they're able to use that same code. Reuse can also be prevalent in using component-based development, right? So breaking out bigger problems into smaller problems and seeing where those smaller functions can be reused and to solve other problems, right? So this is just typical divide and conquer and then build on from there. Everybody wants to reuse, right? It's a secret sauce to making software quickly and cheaply. And there are many factors that promote reuse as well as detract reuse, right? Getting the right knowledge to generalize a software component so that it can be used is difficult, right? But companies and people are encouraged, and IT is encouraged to invest the time in doing that. You have to have sound organizational processes, you have to have skilled people doing this, and you have to have a commitment from senior management. We all know it's easier said than done, but this is what's needed to enable reuse. But the benefits are great. There are investments necessary to do this, but you start to see you start to see benefits if you can do this at a fairly exponential level, right? So it's not it's not for nothing. Let's put it that way. And what it really is doing is one or more of these three things, right? Abstracting, which means making a function generic from a software standpoint, so that you can design it in a more uniform way, clean way, thereby actually helping clean up some of those business processes that are behind the scenes and creating reusable software. So huge economies of scale there. Storage is another area, making software assets available for others to use. So this is the impetus behind cloud, right? Cloud basically promises storage off of the client's computers or systems or infrastructure into the vendor's infrastructure, and making that software asset available for one or more clients to use, right? So kind of solving the storage and the processing issue by taking ownership of it, right? And this is what vendors like Microsoft, Oracle, SAP are doing increasingly. And the last thing, and that's kind of inherent in number one and number two here, is the recontextualization, which is making the software understandable to developers, right? So making it, using some of the more sophisticated programming techniques, using some of the more sophisticated delivery techniques of that software, so that developers are able to pick it up from one team to another and enable that reuse. I think the IT group has a long way to go still on number three. They're busy trying to fix number one and number two, or trying to enable number one and number two. But these are the three different aspects of and steps of software reuse. You can do this on an ad hoc basis. You can facilitate it by design. You can manage to it. You can kind of fix the problems of before and make them make software a little bit more reusable. Obviously, when you do it up front, if it's designed, when assets are mandated for reuse for specific applications, it's the cheapest way to ensure reuse. You do it from the beginning. There's many approaches to this. There's no one way to do it, but increasingly you're going to see people do this a lot and focus a lot on reuse than ever before because of costs. Costs have been very high, and the technology is there. The language proliferation and language advancements are there. Everything is ripe. People just have to do their job better, so to speak, to enable reuse, right? Laziness and this reuse, there's no excuse for laziness, and reuse requires some thinking and some thought. And if you do it later, it obviously costs more to ensure the cleanup, but I know that companies are engaged in one of these four things from the get-go, right? And just to talk a little bit more about that, right, is obviously ad hoc requires no policies and procedures. It's just you just do it as you see fit. And when you design for it, you have to force the organization, but there also, that comes with a high level of reuse because you're baking it in. Whereas ad hoc, you can try it, but it might be reused by one department or in a more micro level way, not in a macro way. And so obviously the further down you go on this list, the more expensive it is in the short run, but more profitable it is in the long run, right? So that's a bit about systems, hardware, and software. Large focus here I spent on was software, and in particular, the different languages and the evolution of how software has come so far and where it's going. So I hope this was informative. Please do join in for the next recorded section that becomes available. We'll be talking about data next, so stay tuned. Take care. Thank you for listening.